Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent passage of an interstellar visitor, a comet born beyond our sun's influence, now approaching Mars in the stillness of early 2025. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The comet designated 3 Ice/Atlas moves through the inner solar system at 23 kilometers per second, though from Earth no motion registers to the naked eye. It appears as a faint smudge in moderate telescopes, a blur of reflected sunlight against the background of more distant stars. The object itself measures perhaps 4 kilometers across its longest axis, a tumbling nucleus of ice and organic compounds that formed not here, not in the planetary disk that gave birth to Mars and Earth, but somewhere in the vast molecular clouds between stars, somewhere else entirely. Only the third confirmed interstellar object to pass through our solar system. It carries in its frozen core the chemical fingerprints of a stellar nursery humans will never see. The ice remembers a different collapse of gas and dust, perhaps 4 billion years ago, perhaps longer. The exact birthplace remains unknown and unknowable. The comet does not keep records. It simply moves, obeying gravity's patient geometry. Astronomers detected it first in October 2024 using the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of robotic telescopes designed to find objects on collision courses with Earth. The irony sits quietly in the data. This particular visitor poses no threat whatsoever. Its orbit, calculated and recalculated with increasing precision over subsequent weeks, describes a hyperbolic path. It will pass through the inner system exactly once, then depart into interstellar space, never to return. The sun cannot hold it. The planets cannot deflect it into captivity. It remains a guest, not a resident. By January 2025, orbital mechanics place the comet on a trajectory that will bring it within 0.089 astronomical units of Mars, approximately 13 million kilometers, measured center to center, close. By the standards of celestial near misses, far. By any measure a human mind might apply to distance, close enough to matter, far enough to remain invisible to the rovers crawling across Martian soil. The comet does not know Mars exists. Mars does not anticipate the comet's approach. Both objects follow their separate mathematics through vacuum, bound by gravitational fields they cannot perceive and do not resist. The physics requires no awareness. The passage will occur whether witnessed or not. As January deepens, the comet accelerates toward perihelion, its closest approach to the Sun. Scheduled for late February, the increasing solar radiation begins to sublime ice from the nucleus surface, water molecules, carbon monoxide, carbon dioxide, methane. All the volatile ices that survived millions of years in interstellar cold now yield to warmth, transforming directly from solid to gas without passing through liquid state. The released gases form a tenuous atmosphere around the nucleus, a structure called the coma, extending thousands of kilometers in every direction. Within this coma, solar ultraviolet light strips electrons from gas molecules, creating a population of charged particles, plasma, the solar wind, a continuous stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Encounters this plasma. The interaction creates an invisible boundary, a shock front where the solar wind abruptly slows and diverts around the obstacle. The comet develops a magnetosphere not from any internal magnetic field, but from the draping of interplanetary magnetic field lines around its expanding coma, an induced magnetosphere, a temporary architecture of electromagnetic force that will dissolve when the comet retreats beyond the sun's influence. No sound accompanies any of this. The coma exists at densities far below Earth's atmosphere at sea level, billions of particles per cubic centimeter, which sounds substantial until one remembers that sea-level air contains trillions of particles in the same volume. The comet's atmosphere remains effectively vacuum by terrestrial standards. Collisions between particles occur, but too infrequently to propagate pressure waves. There is no medium for sound. The shock front forms in utter silence. Mars, meanwhile, continues its own orbit. Utterly indifferent. The planet completes one rotation every 24 hours and 37 minutes, only slightly longer than Earth's day. In early 2025, the Northern Hemisphere experiences spring, though the seasons on Mars stretch nearly twice as long as Earth's due to the planet's longer year. Dust devils spiral across Jezero crater, where Perseverance rover pauses in its sample collection. The thin atmosphere, less than 1% the density of Earth's, shifts with diurnal temperature changes. At night, carbon dioxide freezes directly onto the surface as frost. At dawn, it sublimes back into gas. The planet breathes slowly. The ionosphere exists as a tenuous layer of charged particles high above the surface, created where solar ultraviolet radiation strips electrons from atmospheric molecules. Mars possesses no global magnetic field. Its internal dynamo died billions of years ago, but patchy remnants survive in the crust. Frozen magnetization from an ancient era when molten iron still churned in the core. These crustal anomalies create localized magnetic umbrellas over certain regions, offering partial protection from the solar wind. The rest of the planet remains exposed. Over billions of years, the solar wind has stripped away much of what was once a thicker atmosphere. The erosion continues, grain by grain. Too slow to measure in human lifetimes but relentless across geological time, the planet does not anticipate disruption. The mathematical certainty of the comet's approach exists only in computational models running on Earth-based computers and in the orbital predictions transmitted to spacecraft. The MAVEN orbiter, circling Mars in an elliptical path that dips into the upper atmosphere, continues its measurements of atmospheric escape. The radiation monitors aboard Perseverance continue their patient accumulation of dosimetry data. Both instruments will record the passage, though neither was designed specifically for this encounter. The comet continues inward. Its hyperbolic orbit arcs sunward at an inclination of 47 degrees to the ecliptic plane, the imaginary flat surface on which Earth and most planets orbit. The trajectory crosses that plane at a shallow angle, passing above it, then below. A graceful, tilted swoop through three-dimensional space that will bring it closest to Mars on January 19, 2025, before continuing toward perihelion 5 weeks later. In the nucleus, ice sublimates preferentially from sun-facing surfaces, creating jet-like eruptions that slightly alter the comet's trajectory. These non-gravitational forces complicate orbital predictions, but remain small enough that astronomers update their calculations weekly, refining the predicted closest approach distance with each new observation. The uncertainty shrinks as the encounter date nears. By early January, the predicted miss distance holds steady, 0.089 AU, give or take a few 100,000 kilometers. Close, very close, for objects moving at interplanetary speeds. The comet does not hurry. The comet cannot slow down. It simply approaches, governed by momentum and gravity, carrying ice older than the oldest rocks on Earth toward a world that lost its oceans 3 billion years ago. The mathematics governing the comet's trajectory exist independent of human observation. Though humans perform the calculations anyway, orbital mechanics reduces celestial motion to differential equations, gravity's influence expressed as changes in position and velocity over time. For objects bound to the Sun, orbits trace ellipses, circles, or in rare cases, parabolas. For interstellar visitors like 3I/Atlas, the path describes a hyperbola, a curve that approaches but never meets two asymptotic lines extending toward infinity. The orbital eccentricity measures how elongated a trajectory is. Circles have eccentricity 0. Ellipses range between 0 and 1. Parabolas sit exactly at 1. Hyperbolas exceed 1. The comet 3I/Atlas possesses an eccentricity of approximately 1, 4, calculated from observations of its position against background stars over successive nights. This single number contains the comet's entire future. It will leave the solar system forever. No gravitational perturbation from any planet can reduce that eccentricity below 1. The mathematics forbids return. Astronomers calculate the orbital elements using observations spanning weeks. Each telescope image captures the comet's position at a specific moment, right ascension and declination, coordinates on the celestial sphere, string enough positions together across time, and software can fit a best estimate orbit to the data. The uncertainties shrink with each additional observation. By late December 2024, the orbit is known well enough to predict the Mars encounter with confidence. The closest approach will occur on January 19, 2025, at approximately 14:37 UTC. The uncertainty at that point measures perhaps 20 minutes, trivial across interplanetary distances, yet still too imprecise to calculate electromagnetic effects in advance. The comet arrives from the direction of the constellation Lyra, angling downward through the ecliptic plane as it falls sunward. Its velocity relative to the Sun reaches 23 kilometers per second at Mars's orbital distance, though this speed changes continuously as solar gravity accelerates it. By perihelion in late February, the comet will reach 40 kilometers per second before gravity begins losing its grip as the object climbs back out of the Sun's potential well. The numbers emerge from straightforward Newtonian mechanics, the same equations that govern falling apples and orbiting moons. Scale changes nothing about the underlying physics, only the consequences differ. Mars itself orbits the Sun at 24 kilometers per second, measured along its own elliptical path. The encounter geometry means the comet approaches Mars nearly head-on, the two objects rushing toward the same region of space from different angles. Their relative velocity at closest approach will exceed 30 kilometers per second. Not a collision. The 13 million kilometer miss distance precludes that entirely, but fast enough that electromagnetic interactions, should they occur, will unfold across minutes rather than hours. The hyperbolic excess velocity, the speed the comet will retain even infinitely far from the Sun, calculates to roughly 11 kilometers per second. This represents the comet's motion through the local interstellar medium before it encountered our solar system. The galaxy rotates. Stars orbit the galactic center at different speeds depending on their distance from the core, and the interstellar medium drifts with its own complex flow patterns. The comet moves through all of this, a tiny speck of ice carrying its birth velocity, plus whatever perturbations it accumulated during millions of years, wandering between stars. Precisely where it came from remains unknown. Backtracking the orbit identifies a general direction, but no specific source star. The uncertainties grow enormous over interstellar distances. Perhaps it originated in a stellar nursery 10 parsecs away, perhaps 100. Perhaps it was ejected from a planetary system forming around a young star 2 million years ago, or 20 million. The ice does not record its own history. Only chemistry offers clues, and those remain ambiguous. The three-body problem, predicting the motion of three mutually gravitating objects, has no general analytical solution. Newton proved this indirectly by failing to solve it. For the comet, Sun, and Mars, numerical integration suffices. Computers divide time into small steps, calculating gravitational forces at each instant and updating positions and velocities accordingly. The method accumulates small errors, but over the time scales relevant to this encounter. The predictions hold. The comet will pass Mars on January 19th. The math is certain. The electromagnetic consequences are not. Orbital inclination. The tilt of the comet's path relative to the ecliptic plane measures 47 degrees. Most solar system objects orbit in roughly the same plane, a legacy of the protoplanetary disk from which they formed. Interstellar visitors show no such preference. They arrive from random directions, their inclinations reflecting the three-dimensional geometry of the galaxy rather than the flattened disk of our planetary system. The high inclination of 3I/Atlas marks it as foreign, a trajectory that could never have originated from within the Sun's gravitational domain. The argument of perihelion, the longitude of the ascending node, the time of perihelion passage, all the classical orbital elements emerge from observation and calculation. Each parameter describes one aspect of the trajectory. Together they specify the orbit completely. Any observer with sufficient data could reproduce these numbers independently. The orbit exists as a mathematical object, indifferent to who calculates it or whether anyone bothers at all. Close approach parameters receive special attention: the minimum distance, the time of closest approach, the relative velocity, the geometry of the encounter. Mission planners at NASA and ESA examine these values to determine whether spacecraft instruments might detect anything unusual. MAVEN, in particular, occupies an ideal position. Its elliptical orbit around Mars carries it through the upper atmosphere on each pass, measuring ionospheric properties continuously. If the comet's passage disturbs Mars's ionosphere, MAVEN should record the changes. The predicted electromagnetic effects remain uncertain. Models suggest the comet's induced magnetosphere might extend several 100,000 kilometers from its nucleus. Mars sits 13 million kilometers away at closest approach, far beyond direct contact with the coma. But magnetic field lines connect across vast distances. The interplanetary magnetic field, draped around both the comet and Mars, could provide a pathway for electromagnetic coupling, or it might not. The physics of such interactions scales with distance in complex ways. Published papers offer contradictory predictions. One certainty persists: the encounter will produce no gravitational effects worth measuring. 30 million kilometers vastly exceeds the distance at which a 4-kilometer comet nucleus could perturb Mars's orbit detectably. The tidal forces, already negligible, diminish with the cube of distance. The comet's mass, perhaps a few trillion kilograms, remains microscopic compared to Mars's 600 billion trillion kilograms. Gravitationally, the passage means nothing. Only electromagnetic interactions matter, and those depend on plasma physics too complex for simple prediction. The comet continues its calculated fall toward perihelion. Every hour carries it thousands of kilometers closer to the Sun. Every hour, more ice sublimes from its surface. Every hour. The coma expands and the induced magnetosphere grows stronger. The trajectory does not deviate. The hyperbola remains hyperbolic. Mathematics governs motion with perfect indifference. Mars rotates beneath its thin veil of atmosphere, completing each day in 24 hours, 37 minutes, and 22 seconds. The extra 37 minutes accumulate after 37 Earth days. A Martian clock shows one full day more than an Earth clock started simultaneously. Time moves at the same rate, but the planetary rotations measure it differently. The irony of this hardly registers. Both planets spin, indifferent to synchronization. In January 2025, the Northern Hemisphere experiences late spring. Though the season lacks the associations Earth dwellers might expect, no greening occurs, no flowers bloom. The polar cap, frozen carbon dioxide layered over water ice, has retreated to its summer minimum, exposing dark regolith that absorbs sunlight and warms fractionally. Temperatures at the equator might reach 15 degrees Celsius at local noon in sheltered locations, though they plunge to -80 by dawn. The atmosphere, mostly carbon dioxide with traces of nitrogen and argon, exerts less than 1% of Earth's sea level pressure. Standing on the surface would feel like standing at 40 kilometers altitude on Earth, a height where pressure suits fail and blood boils. The wind blows constantly but gently. Even hurricane-force winds on Mars carry little kinetic energy due to the thin air. Dust devils spiral across plains and crater floors, visible primarily through the dust they loft rather than through any destructive power. The largest storms, planet-encircling dust events that occur every few Martian years, can darken the sky for months. But January 2025 remains clear. Perseverance rover's cameras show crisp horizons under butterscotch skies. The ionosphere begins roughly 100 kilometers above the surface, where solar ultraviolet radiation grows intense enough to strip electrons from atmospheric molecules. The freed electrons create a plasma layer, charged particles that reflect radio waves and interact with magnetic fields. On Earth, the ionosphere enables long-distance radio communication by bouncing signals around the planet's curvature. On Mars, the ionosphere exists more tenuously, its density varying with solar activity and time of day. It offers no services. It simply exists, a consequence of sunlight meeting gas. Mars lacks a global magnetic field, a protective bubble that might shield its atmosphere from the solar wind. Earth's magnetic field extends tens of thousands of kilometers into space, deflecting charged particles and preventing atmospheric erosion. Mars lost its dynamo approximately 4 billion years ago when its core cooled enough that convection ceased. The molten iron stopped circulating. The magnetic field collapsed within perhaps a few million years, geologically instantaneous. Though a human lifetime repeated 100,000 times, what remains are magnetic anomalies frozen into ancient crust, primarily in the southern highlands. These patches of magnetized rock create localized fields strong enough to deflect the solar wind slightly, forming miniature magnetospheres called magnetic umbrellas. They protect nothing. The atmosphere above them escapes no slower than atmosphere elsewhere. The umbrellas merely create interesting structure in the plasma environment, detected by spacecraft instruments but invisible to any observer lacking magnetometers. The solar wind impacts Mars directly across most of its surface. Charged particles slam into the upper atmosphere at hundreds of kilometers per second, transferring momentum to atmospheric molecules. Some molecules gain enough energy to escape Mars's gravity entirely, lost to space. The process strips perhaps 100 grams per second from the planet, negligible on human timescales, catastrophic over billions of years. Mars once possessed a thicker atmosphere, perhaps dense enough to support liquid water on its surface. The solar wind took it, particle by particle, across geological ages. The MAVEN spacecraft, Mars Atmosphere and Volatile Evolution, orbits specifically to study this atmospheric escape. Launched in 2013, it reached Mars in 2014 and has measured the upper atmosphere continuously since. Its elliptical orbit dips to 150 kilometers altitude at periapsis, low enough to directly sample atmospheric gases, then climbs to 6,000 kilometers at apoapsis, high enough to measure the extended hydrogen corona that surrounds the planet, every 4.5 hours. MAVEN completes one orbit, gathering data that accumulates into a decade-long record of how Mars loses its air. On January 19, 2025, MAVEN will be in orbit position 58,394 or thereabouts. The exact count depending on minor orbital adjustments executed in preceding weeks. The spacecraft knows nothing of the approaching comet. Its instruments measure what they always measure: neutral particle composition, ion densities, magnetic field strength, and direction. Solar wind flux. The data streams to Earth via X-band radio transmission, received by the Deep Space Network's 34-meter antennas. Mission scientists examine the data during normal working hours, nights and weekends. The data accumulates in storage, waiting. Perseverance rover, meanwhile, explores Jezero crater at the planet's surface. The crater formed roughly 3.5 billion years ago when an asteroid impact excavated a bowl 45 kilometers across. Later, water carved channels through the crater's western rim, feeding a lake that persisted for perhaps millions of years. Sediments accumulated, deltas formed, then the water disappeared, evaporated or frozen into subsurface ice, leaving behind dried mud and wind-sculpted rock. Perseverance arrived in February 2021 to search those rocks for signs of ancient microbial life. The rover carries a radiation monitoring instrument called MARDI. Mars Environmental Dynamics analyzes radiation and dust sensor. Originally designed to measure background radiation levels for future human mission planning, the instrument tracks charged particle flux continuously. Cosmic rays register as sporadic spikes. Solar energetic particle events create sustained increases lasting hours or days. The detector cannot distinguish particle types without additional analysis, but it counts reliably, accumulating a statistical record of Mars's radiation environment. On January 19th, MARDI will be collecting data just as it does every day. Unaware that anything unusual approaches, the rover's computer follows its programmed schedule: drive a few meters, stop, analyze rocks with spectrometers and cameras, drill samples if conditions warrant, communicate with orbiters passing overhead twice daily. The software contains no provisions for comet encounters. The radiation sensor will record whatever occurs, whether nominal or anomalous. The planet continues rotating. The atmosphere continues escaping, molecule by molecule, into vacuum. The ionosphere fluctuates with the day-night cycle, dense at noon beneath direct sunlight, nearly absent on the night side where darkness permits ions and electrons to recombine into neutral atoms. Mars knows nothing of what approaches from the direction of Lyra. The planet possesses no awareness to know with. It simply exists in dynamic equilibrium, slowly losing its air to space, warmed by sunlight and cooled by radiation to darkness, spinning through January toward an encounter it cannot anticipate. The nucleus of 3I/Atlas holds chemistry pristine beyond anything found in solar system comets. Samples will never be returned. The trajectory precludes rendezvous missions, and even if attempted, the comet will exit the solar system long before spacecraft could be designed, built, launched, and navigated to intercept. What astronomers know? They know from spectroscopy, light passing through the coma, absorbed at wavelengths characteristic of specific molecules. Water ice dominates. As expected, H2O sublimes readily under solar heating, creating the primary component of the coma. But mixed throughout the nucleus are molecules that tell stories about conditions in the comet's birth cloud. Carbon monoxide. Frozen at temperatures below -240 Celsius, sublimates only when sunlight warms the nucleus substantially. Carbon dioxide exists in two forms: mixed with water ice and as pure deposits in colder regions. Methane appears in trace amounts. So does ammonia. Each molecule froze under specific temperature and pressure conditions in the interstellar medium, then remained frozen for millions or billions of years. Spectroscopic observations detect emissions from hydrogen cyanide, formaldehyde, methanol, These molecules form in the gas phase in molecular clouds through reactions between simpler species: hydrogen, carbon, nitrogen, oxygen, catalyzed by dust grains that serve as surfaces where atoms meet and bond. The chemistry proceeds slowly at the 10 Kelvin temperatures typical of dense molecular clouds, but time remains abundant, over hundreds of thousands of years. Complex organic molecules accumulate in the gas and eventually freeze onto dust grain surfaces. When enough ice-coated dust aggregates, a comet nucleus forms. The deuterium to hydrogen ratio in the comet's water provides clues about formation temperature. Deuterium, heavy hydrogen with one proton and one neutron rather than just one proton, gets preferentially incorporated into molecules at very low temperatures through subtle differences in reaction rates. Measurements from other comets show DH ratios varying by factors of 2 or 3, suggesting formation in regions with different thermal histories. Initial spectra from 3I/Atlas suggest a DH ratio toward the high end of the range, consistent with formation in a particularly cold molecular cloud environment. But the measurements remain preliminary. Ground-based telescopes struggle to resolve weak molecular lines against the comet's continuum brightness. Organic chemistry in space favors certain molecules over others based on available reaction pathways. Hydrogen cyanide polymerizes readily, forming more complex nitrogen-bearing organics. Formaldehyde serves as a precursor to sugars through the Formosa reaction, though whether this occurs in comets remains unknown. Methanol ices can undergo ultraviolet-driven reactions that produce methyl formate and other esters. The nucleus contains a frozen organic chemistry laboratory, dormant until sunlight arrives to provide energy. No amino acids have been detected spectroscopically. They lack strong emission lines in accessible wavelength ranges. But meteorite studies confirm amino acids form in cold interstellar environments. The Murchison meteorite, which fell in Australia in 1969, contained over 90 amino acids, most not found in terrestrial biology. If amino acids exist in meteorites, they almost certainly exist in comets. The molecules simply await discovery through future sample return missions or more sensitive spectroscopy. The puzzle of interstellar comet composition centers on what differs from solar system comets versus what remains the same. Early predictions suggested interstellar comets might show exotic chemistry, reflecting formation around stars with different metallicities or in molecular clouds with unusual isotopic ratios. So far, the few interstellar objects detected spectroscopically, primarily 2I/Borisov, the second confirmed interstellar comet, show compositions remarkably similar to solar system comets: water ice, carbon monoxide, carbon dioxide, methanol, hydrogen cyanide. The same molecules appear at similar abundances. This similarity suggests either that comet formation follows universal chemical pathways regardless of birth environment, or that the sample size remains too small to reveal variations. Only 3 confirmed interstellar objects have passed through the inner solar system: 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I/Atlas in 2025. Statistical analysis of 3 data points reveals essentially nothing about population-wide trends. Perhaps the 4th, 5th, and 20th interstellar visitors will show wildly different chemistry. Perhaps not. One mystery persists regarding the organic molecules: their chirality. Many organic molecules exist in mirror image forms called enantiomers, left-handed and right-handed versions that are chemically identical but geometrically distinct. Terrestrial biology uses exclusively left-handed amino acids and right-handed sugars. Whether this preference originated on Earth or arrived from space via comet impacts remains debated. If comets show preferential chirality in their organics, It might indicate that life's handedness was predetermined by interstellar chemistry rather than random chance during life's origin. Unfortunately, chirality cannot be measured spectroscopically from Earth. The technique requires physical samples analyzed in laboratories. For solar system comets, sample return missions like Stardust have brought back comet dust particles, but analyzing them for chiral molecules proves difficult due to contamination concerns and the tiny sample masses. For interstellar comets, no sample return will occur. The chirality question remains unresolved. The nucleus continues its transformation. Closer to the Sun means more solar radiation intercepted per second. More radiation means higher temperatures. Higher temperatures mean faster sublimation. The coma grows denser and more extensive. By mid-January, it extends perhaps 500,000 kilometers from the nucleus, larger than the distance from Earth to the Moon, yet still effectively vacuumed by terrestrial standards. Within this tenuous cloud, molecules absorb sunlight, fluoresce, and emit the spectral signatures that Earth-based telescopes detect. The dust mixed with ice also sublimates, not the dust itself, but the ice bonding dust grains together. As ice vaporizes, it releases dust particles that drift outward under radiation pressure, forming the dust tail. Larger particles drift slowly, smaller ones faster, creating the characteristic curved tail that appears in photographs. The ion tail forms separately when solar wind drags ionized gas molecules outward along magnetic field lines, creating a straighter, bluer tail pointing directly away from the Sun. The comet possesses both tails now, faintly visible in long exposure images from Earth. The dust tail glows by reflected sunlight, yellow-white, broad, and gently curved. The ion tail fluoresces in ultraviolet and blue wavelengths as energetic photons excite carbon monoxide ions, which then emit light as they return to ground state. Neither tail touches anything. Both simply stream behind the nucleus, markers of outgassing and solar wind interaction. The chemistry frozen in the nucleus will largely survive its passage through the inner solar system. Only surface layers will sublime completely. The interior, insulated by overlying ice, will remain frozen even at perihelion. When the comet recedes sunward, outgassing will cease, the coma will dissipate, and the nucleus will return to the frigid conditions of deep space, carrying its pristine interstellar chemistry outward forever. The shock front begins forming when the expanding coma encounters the solar wind at sufficient density to present an obstacle. This occurs gradually, not as a sudden event. The coma extends farther each day as outgassing intensifies. The solar wind flows continuously outward from the Sun at 400 to 700 kilometers per second, depending on whether the current originates from the Sun's equatorial regions or from fast streams emerging from polar coronal holes. The two fluids, one neutral gas sublimating from ice, one ionized plasma streaming from a star, meet in space at a boundary governed by magnetohydrodynamics. The solar wind consists primarily of protons and electrons with trace amounts of heavier ions, helium nuclei, oxygen ions, carbon ions. The particles carry the Sun's magnetic field frozen into the flow, a phenomenon called the frozen-in condition, where plasma flows, magnetic field lines flow with it, draped and stretched but never breaking. The interplanetary magnetic field spirals outward from the Sun in a pattern called the Parker spiral, named for physicist Eugene Parker, who predicted its existence in 1958. At Earth's orbital distance, the field strength measures roughly 5 nanoteslas, 50,000 times weaker than a refrigerator magnet, but sufficient to organize plasma behavior across millions of kilometers. As the coma expands, solar ultraviolet radiation ionizes some fraction of its neutral gas molecules. Water molecules lose electrons and become H2O+ ions. Carbon monoxide becomes CO+, carbon dioxide becomes CO2+. These newly created ions immediately begin responding to the interplanetary magnetic field, gyrating around field lines at frequencies determined by their mass and charge. The ions cannot cross field lines. The frozen-in condition prevents it. But they can slide along field lines and drift perpendicular to both the field and any pressure gradients. The solar wind, flowing outward at hundreds of kilometers per second, encounters this growing population of cometary ions. The interaction proceeds through electromagnetic forces, not collisions. Magnetic fields resist compression. When solar wind tries to flow through the ionized coma, the draped interplanetary magnetic field piles up, creating increased field strength on the sunward side of the coma. This magnetic pressure slows the solar wind, just as aerodynamic pressure slows air flowing past an obstacle. At some distance from the nucleus, typically a few 100,000 kilometers for active comets near 1 astronomical unit from the Sun, the solar wind slows from supersonic to subsonic. This transition occurs across a boundary called the bow shock. Upstream of the shock, the solar wind flows faster than the speed at which disturbances propagate through the plasma. Downstream, the flow has slowed below this critical speed. The shock itself spans perhaps 100 kilometers, thin compared to its lateral extent, but thick enough that particles undergo complex acceleration as they cross it. No sound accompanies this process. The term shock derives from supersonic aerodynamics, where shock waves in air create audible compression waves and sometimes sonic booms. But space contains no air. The solar wind shock is a collisionless shock, mediated by electromagnetic interactions rather than particle collisions. Particles upstream of the shock experience rapidly changing electric and magnetic fields as they cross the boundary. Some particles gain enormous energy, accelerated to relativistic speeds. Others simply slow and deflect. The outcome depends on each particle's initial velocity, charge, and mass. The shock shape resembles the bow wave created by a boat moving through water, though the analogy fails in details. Water waves propagate through an incompressible fluid at fixed speed. Plasma waves propagate at speeds depending on local conditions, temperature, density, magnetic field strength. The bow shock around a comet adjusts its shape continuously as coma density and solar wind conditions vary. Sometimes the shock sits far from the nucleus. Other times, it compresses closer. Real-time measurements show fluctuations on timescales of minutes. Downstream of the bow shock lies a region called the cometer sheath, where shocked solar wind flows around the ionized coma. Magnetic field lines drape over the obstacle, creating a boundary called the contact surface between solar wind plasma and cometary plasma. Inside this boundary, the magnetic field comes entirely from external sources, the draped interplanetary field. The comet nucleus possesses no internal magnetic field of its own. The entire structure is induced, temporary, existing only because the solar wind pushes against the ionized coma. For 3I/Atlas in mid-January 2025, the bow shock has formed and extends perhaps 300,000 kilometers sunward of the nucleus. The exact distance fluctuates with solar wind pressure and coma outgassing rate. The shock appears in no telescope. It cannot be photographed. Only in situ measurements by spacecraft flying through it could reveal its presence. And no spacecraft approaches 3I/Atlas. The shock exists invisibly, a boundary in parameter space where particle distributions change abruptly. The shock also acts as a particle accelerator, some solar wind protons, upon encountering the shock's electromagnetic turbulence, gain energy through a process called shock drift acceleration. The rapidly changing magnetic fields at the shock front can boost particle energies by factors of 10 or 100. These energetic particles then stream both upstream and downstream, creating a population of high-energy protons that extends far beyond the shock itself. Ground-based neutron monitors sometimes detect these particles when Earth passes through the shock regions of nearby comets, though the effect remains subtle. The magnetic field topology around the comet grows complex. Field lines draping over the coma from the sunward side sweep backward, forming a magnetotail extending millions of kilometers in the anti-sunward direction. This tail resembles Earth's magnetotail in structure, but differs in origin. Earth's magnetotail forms because the planet's intrinsic magnetic field gets stretched by solar wind flow. The comet's magnetotail forms from external fields draped and carried downstream by shocked solar wind. The distinction matters to plasma physicists even if the resulting configurations look similar. Within the magnetotail, magnetic field lines from opposite sides of the coma sometimes reconnect. Field lines break and rejoin in a different configuration, releasing stored magnetic energy as particle acceleration and plasma heating. Reconnection events occur sporadically, driven by instabilities in the current sheets that separate oppositely directed field lines. Each reconnection event energizes particles and generates plasma waves that propagate through the surrounding medium. None of this makes sound. All of it proceeds in electromagnetic silence. The comet continues sunward, its induced magnetosphere growing stronger as outgassing intensifies. The shock front pushes farther upstream. The magnetotail extends longer behind. The entire structure exists in dynamic equilibrium, continuously adjusting to changing conditions, never quite settling into steady state. The physics operates according to equations known since the mid-20th century. But solutions to those equations resist analytical treatment. Computers model the interactions, but models contain assumptions and approximations. The reality flowing around the comet nucleus exceeds any simulation's resolution. Mars's ionosphere exists in a state that might be called preparedness if the planet possessed intention. It does not. The ionosphere simply responds to whatever stimuli arrive: solar ultraviolet flux, solar wind pressure, crustal magnetic field geometry, lower atmospheric waves propagating upward from the surface. On January 19, 2025, the ionosphere occupies its usual configuration, determined by local Martian time, solar zenith angle, and prevailing space weather conditions. The ionosphere begins where the neutral atmosphere becomes tenuous enough that solar ultraviolet photons can penetrate without being absorbed immediately. On Mars, this occurs around 100 kilometers altitude, though the boundary fluctuates. Below 100 kilometers, collisions between gas molecules happen frequently enough to recombine ions and electrons back into neutral atoms faster than ionization creates them. Above 100 kilometers, collisions become rare. Ions and electrons persist for hours after being created, drifting under the influence of electric and magnetic fields. The primary ionization process involves carbon dioxide, which constitutes 95% of Mars's atmosphere. A CO2 molecule absorbs an ultraviolet photon with wavelength shorter than about 90 nanometers. The absorbed energy exceeds the molecule's ionization energy. An electron escapes. What remains is a CO2 plus ion, a molecule missing one electron, carrying a net positive charge. The freed electron and the ion both become part of the plasma population, responding to electromagnetic forces rather than simple gas pressure. Peak ionospheric density on Mars occurs around 130 kilometers altitude during local noon, where the solar zenith angle is smallest and ultraviolet flux peaks. Typical electron densities there reach 100,000 to several 100,000 electrons per cubic centimeter, dense by space plasma standards, yet still rarefied compared to Earth's ionosphere, which peaks at 1,000,000 electrons per cubic centimeter. The lower density reflects Mars's thinner atmosphere and weaker gravitational retention of atmospheric gases. At night, ionization ceases. No sunlight means no photoionization. The ionosphere decays through recombination. Ions and electrons collide and neutralize. The decay timescale depends on altitude. At lower altitudes where neutral gas density is higher, collisions occur frequently and the ionosphere vanishes within an hour or two after sunset. At higher altitudes, recombination proceeds more slowly. A residual night-side ionosphere persists with densities 10 to 100 times lower than dayside values. The ionosphere interacts continuously with the solar wind, which strikes Mars directly due to the planet's lack of a global magnetic field. Earth's magnetosphere deflects most solar wind around the planet, allowing only a small fraction to reach the ionosphere at high latitudes. Mars enjoys no such protection. Solar wind impacts the dayside ionosphere continuously, compressing it, removing material through a process called ionospheric sputtering, and depositing energy that heats the upper atmosphere. Where Mars possesses crustal magnetic anomalies, primarily in the southern highlands, the interaction changes character. The localized magnetic fields create mini-magnetospheres that partially shield the underlying ionosphere from direct solar wind impact. Measurements show that ionospheric densities above strongly magnetized crust differ from densities above unmagnetized regions. Though the effect is modest, perhaps 20 or 30% enhancement, the crustal fields are simply too weak to provide comprehensive protection. Magnetic field lines in these mini-magnetospheres can connect to the interplanetary magnetic field through a process called magnetic reconnection. When reconnection occurs, it opens a pathway for solar wind plasma to flow directly along field lines into the ionosphere. This creates localized regions of enhanced plasma flow and particle precipitation. The ionosphere responds by heating and expanding. Turbulence develops. Plasma waves propagate through the disturbed regions, scattering particles and creating additional ionization through electron impact. The ionosphere also responds to waves propagating upward from the lower atmosphere. Gravity waves, atmospheric oscillations driven by buoyancy forces, carry energy from the surface to the upper atmosphere. When these waves reach altitudes where the atmosphere grows tenuous, the wave amplitudes increase dramatically. Eventually, the waves break, depositing their energy as heat and creating turbulence. The ionosphere couples to these neutral atmosphere dynamics, its density fluctuating in response to temperature changes and neutral wind patterns driven by wave activity. MAVEN measures all of this continuously. The spacecraft's neutral gas and ion mass spectrometer identifies individual ion species and measures their abundances. The Langmuir probe and waves instrument measures electron density and temperature. The magnetometer tracks magnetic field variations. During each orbit, MAVEN descends through the ionosphere, collecting vertical profiles of plasma properties, then climbs back to high altitude where it measures the transition to the solar wind-dominated regime. Over 10 years of operations, MAVEN has observed the ionosphere in essentially all configurations, day and night, solar minimum and solar maximum, with and without solar storms, above magnetized and unmagnetized crust. The dataset enables scientists to distinguish typical behavior from anomalous events. On January 19th, the spacecraft will collect ionospheric data just as it has collected data on thousands of previous orbits. The instruments will record whatever occurs. The ionosphere possesses no memory of past disturbances. Each sunset, it decays. Each sunrise, it reforms. The plasma population turns over completely every few hours through the combined effects of ionization and recombination. No particle that exists in the ionosphere on January 18th will remain ionized on January 20th. The structure persists, but the constituents do not. It resembles a waterfall, always present, always flowing. Never the same water twice. If the approaching comet's induced magnetosphere interacts with Mars's ionosphere, the disturbance will appear in MAVEN's data as anomalies in plasma density, temperature, or magnetic field. If no interaction occurs, The data will show typical values consistent with local time, solar zenith angle, and prevailing solar wind conditions. The ionosphere prepares for nothing. It simply exists, moment to moment, responding to whatever forces act upon it. The planet rotates beneath the ionosphere, completing another day. Sunrise moves westward across cratered highlands. The dayside ionosphere strengthens. The nightside ionosphere fades. Solar wind continues its relentless pressure. Atmospheric gases continue their slow escape to space. January 19th approaches, marked on no Martian calendar, anticipated by no Martian awareness, significant only to instruments designed by a different world. The closest approach occurs at 14:37, Coordinated Universal Time on January 19th, 2025. The comet and Mars reach the points in their respective trajectories where the straight-line distance between them reaches its minimum value, 13.3 million kilometers. Center to center. For comparison, Earth's moon orbits at 384,000 kilometers. The comet passes Mars at a distance 35 times the Earth-Moon separation. Close. For solar system encounters. Far. By any human conception of proximity. At that distance, the comet subtends an angular diameter too small to resolve in Mars's sky. The nucleus measures perhaps 4 kilometers across. At 13.3 million kilometers, that corresponds to an angular size of 0.06 arcseconds, far below the diffraction limit of even large telescopes, and utterly invisible to any hypothetical Martian observer looking upward from the surface. The coma extends farther, perhaps 500,000 kilometers in diameter, but even that subtends only 15 arcseconds, comparable to Mars's angular size as seen from Earth during close approaches. The comet would appear, if visible at all, as a faint fuzzy patch in the Martian sky, probably requiring telescopic magnification to detect. But no telescopes exist on Mars pointed skyward. The orbiters carry cameras aimed at the surface or sensors pointed toward the Sun or deep space for navigation. Perseverance's cameras look at rocks and landscapes. No instrument focuses on the region of sky where the comet passes. The encounter goes unwatched by optical means. The geometry places the comet roughly in the direction of the constellation Taurus as seen from Mars. Though constellations vary between planets due to parallax, Mars and Earth sit on opposite sides of the Sun in mid-January 2025, Mars near superior conjunction, meaning the Sun lies almost directly between Earth and Mars from our perspective. Radio communication with Martian spacecraft becomes difficult during superior conjunction due to solar interference, though not impossible if signals route through relay satellites positioned appropriately. The relative velocity at closest approach reaches 32 kilometers per second. If the comet and Mars occupied the same point in space simultaneously, they do not, they would pass each other at this speed. For objects separated by 13 million kilometers, the notion of passing becomes abstract. The distance changes from decreasing to increasing. The moment of minimum separation lasts no time at all, existing only as a mathematical instant. When the derivative of distance with respect to time equals 0, the comet's trajectory carries it below Mars's orbital plane, diving southward at the moment of closest approach. The two objects never occupy the same plane simultaneously. They pass each other in 3 dimensions. Their paths skew lines in space that approach but never intersect. The missed distance represents the shortest segment connecting those skew lines, perpendicular to both trajectories at the instant the segment achieves minimum length. Mars possesses no awareness of the passage. The planet's gravitational field extends infinitely in principle, but diminishes rapidly with distance. At 13 million kilometers, Mars's gravitational acceleration on the comet calculates to approximately 3 × 10⁹ meters per second squared, 3 billionths of the acceleration felt by objects at Earth's surface. Over the several hours near closest approach, this acceleration deflects the comet's trajectory by roughly 100 meters. The deflection remains utterly negligible compared to the uncertainty in knowing the comet's position. The comet, similarly, exerts negligible gravitational influence on Mars. Its mass, perhaps 3 trillion kilograms, produces an acceleration at Mars of roughly 1 x 10 to 14 meters per second squared at closest approach. Integrating this over time yields a total velocity change for Mars of perhaps a few micrometers per second. The planet's orbital velocity around the Sun measures 24 kilometers per second. The comet's passage alters this by 1 part in 10 trillion. Gravitationally, the encounter means nothing. Electromagnetically, the situation grows more complex. The comet's induced magnetosphere extends perhaps 500,000 kilometers from its nucleus, the exact size depending on solar wind conditions and outgassing rate. Mars sits 13 million kilometers away. The magnetospheres do not touch, but magnetic field lines connect across vast distances when conditions permit. The interplanetary magnetic field, draped around the comet and separately around Mars, could provide electromagnetic coupling between the two objects. Field lines from the comet's magnetotail might, under certain geometric configurations, connect to field lines in Mars's induced magnetotail or to the draped field lines around Mars's ionosphere. If such connections form, they would allow charged particles to flow from one region to the other, following field lines across millions of kilometers of otherwise empty space. Whether this occurs depends on the field geometry. The interplanetary magnetic field orientation changes continuously as the Sun rotates and as solar wind conditions vary. At the moment of closest approach, the field might be favorably aligned for connection, or it might not. Models predict both possibilities depending on assumed boundary conditions. The only way to know is to measure. MAVEN's orbit during the encounter carries it through Mars's ionosphere multiple times across the critical hours. The spacecraft's orbital period, 4.5 hours, means it completes portions of 2 or 3 orbits during the window when electromagnetic effects might occur. Each time MAVEN dips into the ionosphere, its instruments sample plasma conditions directly. Each time it climbs to high altitude, it measures the transition between ionosphere and solar wind. The magnetometer aboard MAVEN records magnetic field strength and direction at 8-second intervals. If the comet's passage disturbs the draped field around Mars, the magnetometer should detect changes in field orientation or magnitude. The Langmuir probe measures electron density and temperature. If energetic particles from the comet's shock front reach Mars's ionosphere, electron temperatures should increase detectably. The ion mass spectrometer might detect unusual ion composition if comet origin ions flow along field lines to Mars. Perseverance's radiation detector on the surface faces limitations. It measures total ionizing radiation dose without distinguishing particle types or energies in detail. If the comet's passage enhances the flux of energetic particles reaching Mars, the detector should register an increase in dose rate. But the instrument's sensitivity may not suffice to detect subtle changes against the background of galactic cosmic rays and solar energetic particles always present. The encounter geometry favors dayside observations. At 1437 UTC, Mars's orientation places Jezero crater, Perseverance's location, in late morning local time. The ionosphere above the rover sits in full sunlight, ionized and responsive to any electromagnetic disturbances arriving from the comet's direction. MAVEN, in its elliptical orbit, passes through dayside and nightside ionosphere with each orbit, sampling both environments. Ground-based telescopes on Earth cannot observe Mars during superior conjunction. The planet sits too close to the Sun in Earth's sky, rising and setting with the Sun, invisible in daylight glare. Radio telescopes might attempt observations, but Mars appears as a small radio source compared to the Sun's overwhelming emission. Any signals would require careful filtering and processing. The 13 million kilometers separating Comet and Mars represents a distance light travels in 44 seconds. Information about the comet's electromagnetic state takes 44 seconds to propagate to Mars at light speed. Disturbances in the interplanetary magnetic field travel slower. At the Alfvén speed determined by field strength and plasma density, perhaps a few hundred kilometers per second in the solar wind at Mars's orbital distance, this means magnetic disturbances take hours to propagate across 13 million kilometers. The encounter unfolds slowly by electromagnetic timescales. The comet continues past Mars, its trajectory unchanging. The hyperbolic orbit carries it sunward at 23 kilometers per second. Every hour puts another 80,000 kilometers between the nucleus and the red planet. By midnight UTC on January 19th, the separation exceeds 14 million kilometers. By dawn on January 20th, 15 million. The distance grows without limit, asymptotically approaching the comet's departure trajectory out of the solar system. Mars continues its orbit, 24 kilometers per second around the Sun, completing one revolution every 687 Earth days. The planet has orbited the Sun approximately 2.5 billion times since its formation. This orbit differs from all previous orbits only in that a comet passed 13 million kilometers away at one moment during one day. The difference remains immeasurable by any gravitational metric. Magnetic field lines possess no physical substance. They exist as mathematical constructs representing the direction a compass needle would point at each location in space, or the trajectory a charged particle would follow if it could move without crossing field lines. Nevertheless, these abstract lines behave in specific ways governed by Maxwell's equations and plasma physics. They stretch, compress, drape, and reconnect according to rules as rigorous as those governing the motion of solid objects. Around the comet, field lines from the interplanetary magnetic field drape over the ionized coma like fabric hung over a frame. The solar wind, flowing outward from the Sun and carrying the frozen-in magnetic field with it, encounters the obstacle of the coma and diverts around it. The field lines, unable to penetrate the conducting plasma, bend around the obstacle's sides. On the sunward side, field lines compress together, increasing field strength. On the downstream side, they trail behind the comet in a magneto-tail extending millions of kilometers around Mars. A similar process occurs, though with different boundary conditions. Mars possesses crustal magnetic anomalies that add complexity to the draped field geometry, where crustal fields are strong. They push back against the solar wind, creating localized regions where field lines connect to the planet rather than simply draping over the ionosphere. These mini-magnetospheres occupy perhaps 20% of Mars's surface area, primarily in the southern highlands. Elsewhere, field lines drape over the ionosphere just as they drape over the comet's coma. The possibility of magnetic connection between the comet's magneto-tail and Mars's magnetic environment depends on field line topology. If field lines from the comet's tail happen to align with field lines near Mars, reconnection can occur. Reconnection is a process where oppositely directed field lines approach each other, break, and rejoin in a different configuration. The breaking and rejoining happens through plasma physics processes operating in thin regions called current sheets, where magnetic field direction reverses across distances comparable to a few ion gyro radii, typically hundreds of kilometers in the solar wind. When reconnection occurs, stored magnetic energy converts to particle kinetic energy. Electrons and ions accelerate along the newly reconnected field lines, sometimes reaching relativistic speeds. The accelerated particles then propagate along field lines at velocities far exceeding the bulk plasma flow speed. If a field line connects the comet's environment to Mars's ionosphere through reconnection, particles could stream from one region to the other in minutes despite the 13 million kilometer separation. The geometry on January 19th remains uncertain until measured. The interplanetary magnetic field orientation depends on solar wind source region structure and the Parker spiral angle, which varies with solar rotation. Models predict the field might lie roughly in the ecliptic plane, tilted perhaps 30 degrees from the radial direction at Mars's orbital distance. But solar wind is turbulent. Fluctuations occur on timescales from seconds to hours. The field direction at the moment of closest approach cannot be predicted accurately in advance. MAVEN's magnetometer can measure field direction and strength with high precision. The instrument resolves field components to better than 1 nanotesla, sufficient to detect the subtle changes associated with draping geometry variations. If reconnection occurs near Mars, the magnetometer should detect characteristic signatures, rapid field rotations, enhanced field magnitude in the reconnection exhaust, and elevated plasma temperatures downstream of the reconnection site. The crustal magnetic anomalies on Mars create a patchy field topology. Field lines from some anomalies remain closed, connecting southern and northern magnetic poles within the crust without extending into space. Other field lines open into the solar wind, connecting one foot in the crust and the other extending to infinity. These open field lines provide pathways for solar wind plasma to flow directly into the upper atmosphere, enhanced during periods when the solar wind magnetic field direction aligns favorably for reconnection. If the comet's passage disturbs the large-scale interplanetary field configuration, it might temporarily enhance or suppress reconnection rates at Mars's crustal anomalies. Enhanced reconnection would increase plasma inflow to the ionosphere, raising electron densities and temperatures in localized regions above magnetized crust. Suppressed reconnection would have the opposite effect. The net result depends on the specific field geometry, which varies continuously. The magnetotail structures of both the comet and Mars extend in the anti-sunward direction, roughly aligned but separated by 13 million kilometers perpendicular to that direction. Whether their magnetotails interact electromagnetically depends on whether current sheets from one magnetotail can influence plasma in the other. Currents flowing in the comet's magnetotail create magnetic fields that fall off with distance. At 13 million kilometers, the comet's magnetic field contribution at Mars's location calculates to perhaps a few picoteslas, 3 orders of magnitude below the ambient interplanetary field of a few nanoteslas. Direct field effects appear negligible, but alpha waves, electromagnetic disturbances propagating along field lines, can carry information across larger distances than static field effects. If the comet's shock front generates alpha waves, those waves propagate both upstream and downstream along field lines at the alpha speed. At typical solar wind conditions, alpha speeds reach a few hundred kilometers per second. Waves generated at the comet could reach Mars in 10 to 15 hours if field line geometry permits direct connection. The complexity of the interaction exceeds simple prediction. 3-dimensional magnetohydrodynamic simulations can model field line draping around obstacles and predict where reconnection might occur. But such simulations require knowledge of boundary conditions, solar wind density, velocity, temperature, and magnetic field vector, which remain uncertain until measured. Post-encounter analysis can reconstruct what likely happened. Real-time prediction remains approximate at best. Magnetic topology also affects particle transport. Electrons gyrate around field lines with gyroradii of a few kilometers in the solar wind. Protons gyrate with radii of a few hundred kilometers. Both particle types remain essentially tied to field lines, unable to cross them except through diffusion processes that operate slowly. If a field line connects the comet to Mars, particles can stream along it efficiently. If field lines do not connect, particles must diffuse across field lines to move from one region to the other, a process many orders of magnitude slower. The encounter therefore consists of multiple electromagnetic questions. Does the large-scale field geometry permit direct connection? Do alpha waves generated at the comet's shock front reach Mars? Does the comet's passage alter reconnection rates at Mars's crustal anomalies? Each question requires measurement to answer. Theory provides frameworks, but not definitive predictions. MAVEN orbits, measuring continuously. The magnetometer samples 8 times per second. The Langmuir probe measures electron density every 4 seconds. The data accumulates, transmitted to Earth where it arrives 8 to 20 minutes later, depending on the precise Earth-Mars distance during superior conjunction. Mission scientists monitor the data stream, watching for anomalies. The magnetic field lines stretch, reconnect, and reconfigure according to plasma physics, indifferent to observation. Word count 1,198. Awaiting, continue section 9. The shock front formed by the comet's interaction with the solar wind produces no sound. This fact deserves emphasis precisely because the terminology suggests otherwise. The word shock evokes explosions, sonic booms, violent acoustic disturbances. In space, none of these occur. The shock exists as a discontinuity in plasma parameters: density, temperature, velocity, magnetic field, across which particles experience rapid acceleration or deceleration. The transition occurs silently. Sound requires a medium capable of sustaining compression waves. In Earth's atmosphere, sound propagates as alternating compressions and rarefactions of air molecules. The molecules collide frequently, billions of times per second at sea level, allowing pressure disturbances to propagate as waves. The wave speed depends on temperature and molecular composition, traveling approximately 340 meters per second in standard conditions. Sounds from explosions, thunder, or human speech all propagate through this mechanism. Space possesses no such medium. The solar wind plasma contains particles, but at such low densities that collisions between them occur infrequently. At 1 astronomical unit from the Sun, solar wind density typically measures about 5 particles per cubic centimeter, 5 protons, 5 electrons, perhaps 1 helium nucleus. This sounds substantial until compared to Earth's atmosphere, which contains 2.5 x is 1019 molecules per cubic centimeter at sea level. The solar wind is 14 billion times less dense than sea level air. At such densities, the mean free path, the average distance a particle travels between collisions, exceeds thousands of kilometers. Particles stream through space without touching neighboring particles for hours. Pressure disturbances cannot propagate through collisions because collisions are too rare. Ordinary sound waves cannot exist. The medium is too tenuous. Yet shock fronts do exist in the solar wind, created through electromagnetic interactions rather than collisions. When solar wind encounters the comet's ionized coma, the flowing plasma must slow and deflect. This deceleration happens not through air-like drag, but through electromagnetic forces. The solar wind carries magnetic fields. Those fields resist compression. As solar wind approaches the obstacle, magnetic pressure builds, slowing the flow. The slowing occurs discontinuously at the bow shock, upstream. Solar wind flows supersonically, faster than disturbances can propagate through the plasma, downstream. The flow has decelerated to subsonic speeds. The transition happens across a thin region, perhaps 100 kilometers thick, where electromagnetic forces act on individual particles, changing their velocities abruptly. Particles gyrate around magnetic field lines, bouncing back and forth across the shock front multiple times before finally passing downstream. With each crossing, they gain or lose energy. Some particles gain substantial energy through shock drift acceleration. The exact mechanism involves complex interactions between particles and the time-varying electromagnetic fields at the shock. Particles entering the shock region at certain angles can extract energy from the flowing plasma, accelerating to speeds far exceeding the bulk flow velocity. These energetic particles then stream both upstream and downstream, creating populations of high-energy protons and electrons extending far from the shock itself. No rumble accompanies this process. No thunderclap marks particle acceleration. The electromagnetic fields fluctuate at frequencies far below human hearing, typically millihertz to a few hertz. If converted to sound through some artificial means, the frequencies might produce a deep bass drone. But no conversion mechanism exists. The fields simply vary. Accelerating particles. Releasing energy from the flowing plasma. The violence remains electromagnetic, not acoustic. Mars's interaction with the solar wind produces similar effects. Without a global magnetic field, Mars cannot form a true bow shock far upstream as Earth does. Instead, the solar wind impacts the ionosphere more directly, creating a complex boundary region where plasma physics governs the interaction. Magnetic fields pile up on the day side, creating enhanced field strength in a region called the magnetic pile-up boundary. Upstream of this boundary, a weak shock sometimes forms, though its presence depends on solar wind conditions. During quiet solar wind periods, the shock disappears entirely. The solar wind simply drapes around the ionosphere without forming a well-defined discontinuity. During active periods with strong solar wind pressure, a clear shock develops. Maven has observed both configurations and mapped the transition conditions. The shock, when present, produces no sound. Mars orbits through vacuum, its interaction with the solar wind proceeding silently. If electromagnetic disturbances from the comet's shock front reach Mars's magnetic environment, they will appear as changes in magnetic field measurements and particle distributions. Maven's instruments will record variations in field strength, direction, and associated plasma properties, but the spacecraft's magnetometer and particle detectors respond to electromagnetic fields and charged particle fluxes, not acoustic waves. The data will show electromagnetic signatures or show nothing. No audio recording could capture the event. The human desire to hear space events has driven numerous projects converting electromagnetic data into sound. Plasma waves detected by spacecraft are often frequency shifted into the audible range and played as audio files. These sonifications provide intuitive representations of data, helping researchers identify patterns and anomalies. But the sounds are artificial constructs, not actual acoustic waves detected in space. Space remains silent. This silence extends to everything beyond atmospheres. The sun's fusion reactions release enormous energy but no sound. Fusion occurs in vacuum-like conditions in the core where acoustic waves cannot propagate effectively, and surface convection happens in plasma too tenuous to sustain sound as terrestrial atmospheres do. Supernovae explode silently. Neutron stars collide without acoustic signatures. Galaxies merge over millions of years in utter quiet. Only electromagnetic radiation carries information across cosmic distances. The comet's passage past Mars will add no sound to this silence. The shock fronts, magnetic reconnection events, particle acceleration, and plasma heating all proceed through electromagnetic processes. If humans stood on Mars during the encounter, they do not, they would hear nothing unusual. The thin Martian atmosphere sometimes carries faint sounds from wind or dust devils, but nothing from the comet 13 million kilometers away. The encounter remains inaudible. Maven continues measuring the electromagnetic environment. The instruments do not listen. They sample electric and magnetic fields, count particles, measure energies and velocities. The data streams to Earth as radio transmissions, also electromagnetic, also silent until decoded and displayed as numbers or graphs. The shock exists mathematically, defined by discontinuities in measurable parameters. It produces no sound and needs none to function. The instruments on Mars record what they are designed to record. Nothing more. MAVEN carries 8 instruments, each measuring specific aspects of Mars's upper atmosphere and its interaction with the solar wind. During the hours surrounding closest approach, these instruments sample plasma conditions at their usual cadence, accumulating data that differs from typical observations only if the comet's passage actually disturbs Mars's electromagnetic environment. The magnetometer, mounted on the spacecraft body to minimize interference from onboard systems, measures magnetic field strength in 3 orthogonal directions. The sensor consists of 2 ring-core flux gate magnetometers, one serving as primary and one as backup. The instrument samples at 32 vectors per second, but typically downlinks data average to 8 samples per second to conserve bandwidth. The measurement range extends from 0.01 nanoteslas to 65,536 nanoteslas, far exceeding the expected field strengths in Mars's environment, which typically vary from a few nanoteslas to a few tens of nanoteslas. If the comet's passage alters the draped magnetic field configuration around Mars, the magnetometer will record changes in field components. A sudden rotation in field direction might indicate passage of a current sheet or shock front. An enhancement in field magnitude could signal compression of field lines. Oscillations at specific frequencies might reveal alpha waves propagating from a distant source, or the data might show nothing unusual, field variations within the normal range observed during quiet periods. The Langmuir probe and waves instrument extends from the spacecraft on a 2-meter boom, placing its sensors away from plasma disturbances created by the spacecraft's motion through the ionosphere. The probe measures electron density by detecting the current drawn when the sensor is biased to different voltages. Electron temperature emerges from analyzing how current varies with bias voltage. The instrument also measures electric field waves by detecting voltage fluctuations between sensors during ionospheric passes. The Langmuir probe typically records electron densities ranging from a few hundred per cubic centimeter at high altitudes to several 100,000 per cubic centimeter at the ionospheric peak around 130 kilometers altitude. If energetic particles from the comet's shock front reach Mars, they might enhance ionization, raising electron densities above typical values, or they might heat electrons, raising temperatures detectably, or neither effect might occur if the interaction remains too weak or geometrically unfavorable. The neutral gas and ion mass spectrometer inhales atmospheric gases and ionospheric plasma through a small opening, then uses electromagnetic fields to separate ions by their mass-to-charge ratio. The instrument identifies molecular species, CO2+, O2+, OO+, N2+, AR+, and measures their abundances. The mass resolution suffices to distinguish isotopes: 40R from 36AR, 13C from 12C in carbon dioxide ions. If ions from the comet's coma somehow reach Mars's ionosphere, they would appear as unusual mass peaks. Water ions, H2O+ or H3O+, do not normally appear in Mars's ionosphere in significant quantities. Water vapor is too scarce in the atmosphere. Detection of water group ions during the encounter might indicate comet origin plasma, or it might indicate nothing more than measurement noise or contamination from outgassing spacecraft materials. The Solar Energetic Particle Instrument measures high-energy ions and electrons arriving from the Sun or from other sources. The detector consists of solid-state sensors arranged to determine particle direction, energy, and approximate composition. It records solar energetic particle events produced by solar flares and coronal mass ejections. During quiet periods, it measures the background flux of galactic cosmic rays. If the comet's bow shock accelerates particles to high energies, and if those particles somehow reach Mars, the Solar Energetic Particle Instrument might detect an enhancement in particle flux during the encounter window. The detector cannot determine particle origin directly. Energetic protons from the comet's shock look identical to protons from a solar flare. Only timing, energy spectrum, and angular distribution could suggest an unusual source. The solar wind ion analyzer measures the three-dimensional velocity distribution of solar wind ions. The instrument consists of an electrostatic analyzer that selects ions by energy, followed by a time-of-flight sensor that determines mass. The combination identifies ion species, protons, helium, oxygen, carbon, and measures their flow velocity, temperature, and density. During each MAVEN orbit, the analyzer samples solar wind conditions when the spacecraft flies at high altitudes beyond Mars's bow shock. If the comet's passage disturbs solar wind properties at Mars's orbital location, the solar wind ion analyzer should detect changes. The solar wind might slow, heat, or change direction if a shock front or magnetic structure from the comet passes by, or the measurements might show nominal solar wind, unchanged by events 13 million kilometers away. The suprathermal and thermal ion composition instrument measures ions with energies between a few electron volts and tens of kilo-electron volts, the transition range between cold ionospheric ions and hot solar wind ions. This population includes ions escaping from Mars's atmosphere through various processes: pickup by the solar wind, acceleration in electric fields, sputtering by solar wind impact. The instrument's measurements help quantify atmospheric escape rates. During the encounter, this instrument will continue measuring escaping ions as always. If electromagnetic disturbances enhance escape processes, the measured fluxes might increase. If disturbances somehow suppress escape, fluxes might decrease, or the measurements might show typical values. Atmospheric escape continuing unperturbed regardless of the comet's distant passage. On the surface, Perseverance's radiation and dust sensor measures total ionizing radiation dose using silicon detectors sensitive to charged particles above about 10 mega-electron volts. The instrument records dose rate continuously, accumulating data that documents Mars's surface radiation environment. The detector cannot identify particle types. It simply counts energy deposited in the silicon. If energetic particles generated by the comet's shock front reach Mars in sufficient numbers, the detector might register a transient increase in dose rate above background levels. Background radiation at Mars's surface comes primarily from galactic cosmic rays, which produce a fairly steady dose rate of about 0.2 millisieverts per day. Solar energetic particle events can increase surface dose rates by factors of 2 to 10 for hours or days. A comet-related enhancement might resemble a small solar energetic particle event, or the detector might record nothing unusual. Energetic particles generated 13 million kilometers away might not reach Mars in detectable numbers, or they might arrive but carry too little energy to penetrate Mars's atmosphere to the surface, or geometric factors might prevent them from reaching Jezero crater's location even if they arrive at Mars. All instruments sample, digitize, store, and transmit their data according to program schedules. No instrument knows that January 19th differs from January 18th or January 20th. The measurements accumulate regardless, added to data sets spanning years or decades of continuous observation. The data will reveal what occurred only after analysis, comparison with models, and correlation across instruments. The tail extends behind the comet nucleus across millions of kilometers, though tail suggests a coherent structure that does not quite match reality. Two tails exist simultaneously, each formed by different physical processes and pointing in slightly different directions. One consists of ionized gas molecules swept along magnetic field lines by the solar wind. The other consists of dust particles pushed by solar radiation pressure. Both expand continuously as the comet approaches perihelion, growing longer and brighter as outgassing intensifies. The ion tail forms when solar ultraviolet radiation ionizes molecules in the coma. Carbon monoxide molecules lose electrons and become CO+ ions. The same process affects CO2, H2ON, and other volatile species. Once ionized, the molecules can no longer move freely. They become tied to magnetic field lines through the frozen-in condition. The solar wind, carrying draped magnetic field lines away from the comet in the anti-sunward direction, sweeps ions along with it. The ions accelerate downstream, reaching speeds comparable to the solar wind flow velocity. The ion tail consequently points almost exactly away from the sun, following the local magnetic field direction. Its color, when visible, appears blue-green due to emission from carbon monoxide ions fluorescing under solar ultraviolet excitation. CO+ ions absorb ultraviolet photons and re-emit visible light at characteristic wavelengths around 420 nanometers. Other molecular ions contribute additional emission lines at different wavelengths. The combined spectrum creates the blue-green color seen in photographs. Though the human eye would perceive the tail as faint if observed directly, the ion tail extends perhaps 10 million kilometers behind 3I/Atlas in mid-January, though defining the tail's end proves difficult. Ion density diminishes gradually with distance from the nucleus. At some point, the ion tail becomes indistinguishable from background solar wind plasma. No sharp boundary marks this transition. Photographs show the tail extending as far as light from cometary ions remains detectable above background sky brightness. Structures appear within the ion tail: striations, knots, disconnection events. These features arise from magnetic field instabilities and solar wind variations. When the direction of the interplanetary magnetic field changes abruptly, often due to passage of a solar wind sector boundary or an interplanetary shock, the tail can disconnect entirely. The old tail drifts away, still fluorescing, while a new tail begins forming from fresh ions in the coma. Observations of bright comets sometimes show multiple disconnection events during a single apparition. The dust tail forms through a different mechanism. Ice sublimating from the nucleus releases embedded dust grains, particles ranging from nanometers to millimeters in size. Once released, dust grains follow ballistic trajectories under the influence of solar gravity and radiation pressure. Solar photons striking dust grains impart momentum, pushing particles anti-sunward. The radiation pressure force depends on grain size. Small grains experience stronger acceleration relative to their mass than large grains. This size dependence creates the dust tail's curved shape. Small grains accelerate rapidly anti-sunward, producing the tail's outer edge. Large grains accelerate slowly, remaining closer to the comet's orbital path and forming the inner edge of the dust curve. The resulting tail appears as a broad, curved arc pointing roughly anti-sunward, but lagging the ion tail's direction slightly due to orbital motion. The dust tail glows by reflected sunlight, not through fluorescence. Its color matches the sun's color, yellowish-white, warmer than the blue-green ion tail. The brightness depends on how much dust the nucleus produces and how effectively dust grains scatter sunlight. Dust production rates vary dramatically among comets. Some comets produce predominantly gas with little dust. Others emit dust abundantly. The ratio correlates with nucleus composition and thermal history, but remains difficult to predict without direct observation. For 3I/Atlas, preliminary observations suggest a moderate dust-to-gas ratio, neither extremely dusty nor extremely gas-rich. The dust tail extends perhaps 3 to 4 million kilometers in mid-January, shorter than the ion tail but more visible to small telescopes due to scattered sunlight. The tail will grow as the comet approaches perihelion, when solar heating intensifies and outgassing accelerates. Between the nucleus and the tail structures lies a transition region where outgassing jets create asymmetries. The nucleus rotates. Observations suggest a rotation period of about 15 hours, and ice sublimation occurs preferentially from sun-facing regions. As the nucleus rotates, active regions move in and out of sunlight, creating pulsed gas jets that spiral away from the nucleus due to rotational motion. These jets appear in high-resolution images as fan-shaped structures extending from the coma. The jets carry both gas and dust. Gas molecules expand radially from active areas at velocities near 1 km per second, determined by thermal energy at ice sublimation temperatures. Dust grains, entrained in the gas flow, accelerate until gas drag weakens at larger distances where gas density drops. The heaviest grains never reach high velocities and fall back toward the nucleus, sometimes creating a faint anti-tail pointing sunward, an optical illusion caused by perspective. Both tails sweep through space without touching anything. The ion tail consists of plasma at densities far below laboratory vacuums. The dust tail contains grains separated by thousands of kilometers on average. If Earth passed through a comet tail, this has occurred occasionally, the effect at ground level would be minimal. Some meteors might appear as dust grains burn in the atmosphere. Sensitive instruments might detect trace amounts of cometary gases, but no catastrophe would occur. The tails, despite their impressive visual extent, contain almost no mass. The total mass of ions in a 10 million kilometer ion tail might be only a few thousand kilograms, equivalent to a small car. The dust tail might contain 10 or 100 times more mass, but still negligible compared to the nucleus. The tails represent outgassing products dispersed across enormous volumes. Their visual prominence far exceeds their physical substance. As the comet recedes from perihelion months later, outgassing will decline. The tails will shrink and fade. Eventually, far from the sun, sublimation will cease entirely. The coma will dissipate. The tails will vanish. The nucleus will return to its dormant state, a dark frozen body traveling outward through darkness, its temporary display of tail structures gone as if they never existed. But on January 19th, 2025, the tails extend fully, streaming away from the nucleus as 3I/Atlas passes Mars. The ion tail points anti-sunward, roughly perpendicular to the line connecting comet and planet. The dust tail curves gently in the same general direction. Mars lies to the side, 13 million kilometers from the nucleus. The tails sweep past at a different distance, perhaps 13.5 million kilometers from Mars at their closest point. Depending on the tail's exact geometry, no intersection occurs. The tails do not touch Mars's magnetosphere or atmosphere. They simply exist in space. Ephemeral structures marking the comet's passage, visible to distant telescopes but imperceptible to instruments at Mars focused on other measurements. The encounter proceeds with the comet's tails streaming past in three-dimensional space, beautiful and inconsequential. Earthbound observers watch the comet from 93 million kilometers farther from the Sun than Mars, across Superior Conjunction where Mars sits almost directly behind the Sun from Earth's perspective. The geometry challenges observation. Mars cannot be observed optically. It rises and sets with the Sun, lost in daylight glare. The comet, positioned near Mars in the sky as seen from Earth, similarly sits close to the Sun's overwhelming brightness. Observing requires careful timing and specialized equipment. Amateur astronomers in dark sky locations attempt observations in twilight, either before sunrise or after sunset when the Sun has dipped below the horizon, but the comet still remains above. The window lasts perhaps 30 minutes, the sky dark enough to reveal faint objects, but the comet's altitude above the horizon sufficient for viewing. The comet's brightness in mid-January reaches magnitude 8 or 9, too faint for naked eye visibility but accessible to moderate-sized telescopes under good conditions. Telescopes equipped with CCD cameras capture images during these twilight windows. Exposure times of 30 to 60 seconds integrate enough photons to reveal the comet's coma and perhaps the brightest portion of its tail. The images show a soft, fuzzy blob, slightly elongated if the tail is visible, moving slowly against background stars. Night by night. The comet's position shifts as it continues sunward. Astrometry performed on these images, measuring precise positions against reference stars, contributes to orbital refinement, improving predictions of future positions. Some observers attempt spectroscopy, dispersing the comet's light into spectra that reveal molecular emission lines. Small spectrographs attached to amateur telescopes can detect the bright CN emission band at 388 nanometers and the C2 Swan bands at various wavelengths. More sensitive instruments might detect CO+ emission or other molecular signatures. The spectra provide information about coma composition and gas production rates. Professional astronomers use these data to compare 3 I/Atlas's chemistry with other comets, interstellar and solar system alike. Radio telescopes observe the comet at wavelengths unaffected by sunlight proximity. Molecular emission lines in the millimeter and centimeter wavelength ranges allow detection of species invisible to optical spectroscopy. The hydroxyl radical OH, produced when water molecules photodissociate in sunlight, emits strongly at 18 centimeter wavelength. Carbon monoxide emits at 2.6 millimeters. Methanol shows multiple emission lines in the millimeter range. Hydrogen cyanide emits at 3.4 millimeters. Large radio telescopes. The Green Bank Telescope in West Virginia. The Atacama Large Millimeter Array in Chile. The Nobeyama Radio Observatory in Japan point towards the comet's predicted position and integrate signal over hours. The emissions appear as narrow spectral lines, their frequencies Doppler shifted by the comet's motion relative to Earth. Measuring the line shapes reveals information about gas velocities in the coma. Measuring line intensities allows calculation of molecular abundances and gas production rates. Radio observations proceed unimpeded by daylight. The sun emits radio waves, but at frequencies offset from molecular emission lines. Those solar emissions can be filtered. Observations continue around the clock when the comet is above the horizon, accumulating data that optical telescopes cannot gather during daylight hours. The radio spectra complement optical and ultraviolet observations, building a comprehensive picture of the coma's composition. Space-based telescopes contribute observations free from atmospheric absorption. The Hubble Space Telescope, though designed primarily for optical wavelengths, can observe in near ultraviolet where atmospheric ozone blocks ground-based telescopes. Ultraviolet observations reveal emission from atomic hydrogen in the comet's extended corona, a vast hydrogen cloud surrounding the coma, formed when water molecules dissociate into hydrogen and oxygen. The hydrogen atoms scatter solar ultraviolet light, creating a glow extending millions of kilometers from the nucleus. The James Webb Space Telescope, operating at infrared wavelengths, observes the comet to detect molecular emissions invisible at other wavelengths. Water vapor emits strongly in the infrared. So does carbon dioxide. The telescope's spectroscopic instruments can measure isotopic ratios, deuterium to hydrogen in water, carbon-13 to carbon-12 in carbon dioxide. These measurements constrain models of the comet's formation environment, revealing temperatures and chemical processes in its birth cloud. X-ray observatories occasionally observe bright comets, detecting X-ray emission produced when solar wind ions collide with neutral gas in the coma. The collisions strip electrons from the neutral molecules, and the resulting charge exchange reactions emit X-rays at characteristic energies. The process provides information about solar wind composition and comet outgassing rates simultaneously. For 3 I/Atlas, X-ray observations might be attempted. Though the comet's moderate brightness suggests X-ray emission may remain faint, professional observatories worldwide coordinate observations during the Mars encounter window. The goal is to detect any changes in the comet's behavior coincident with closest approach. Does outgassing rate change? Do molecular abundances shift? Does the coma brighten unexpectedly? Such changes might indicate electromagnetic interaction with Mars or simply coincidental variations in solar wind conditions or nucleus activity. No changes are expected. 13 million kilometers represents a substantial separation, and electromagnetic coupling across that distance seems unlikely based on theoretical models. But observations will reveal whether models correctly predict reality. Science proceeds through measurement, not assumption. Telescopes point, detectors integrate photons, data accumulate. Some observers focus on Mars itself using radio techniques. The Very Large Array in New Mexico can observe Mars at centimeter wavelengths, measuring thermal emission from the planet's surface and atmosphere during superior conjunction. Radio observations remain possible while optical observations do not. Changes in Mars's radio emission during the comet encounter might indicate atmospheric or ionospheric disturbances, though interpreting such changes would require careful analysis to exclude solar interference. Ground-based radar cannot detect the comet. Its small size and large distance place it below detection thresholds for planetary radar systems. But Mars remains radar visible. The Goldstone Solar System radar in California and the Arecibo Observatory, prior to its collapse in 2020 and now unavailable, could illuminate Mars and detect reflections. The delayed Doppler radar imaging technique can map Mars's surface and probe its ionosphere through echo characteristics. Observations during the encounter window might reveal ionospheric disturbances if they occur. Amateur radio observers occasionally detect Martian atmospheric phenomena by monitoring spacecraft transmissions. When orbiters or rovers transmit signals to Earth, those signals pass through Mars's atmosphere and ionosphere. Variations in signal strength or frequency can indicate atmospheric conditions along the propagation path. During the comet encounter, amateur stations equipped with large antennas might attempt to monitor signals from MAVEN or Perseverance, looking for anomalies correlating with the closest approach time. The observations generate data, but not immediate answers. Telescope images show the comet's position and brightness. Spectra reveal molecular emissions. Radio measurements quantify gas production. But whether the comet interacts electromagnetically with Mars cannot be determined from Earth-based observations of the comet alone. The observations document the comet's state before, during, and after the encounter. Only Mars-based measurements can reveal whether Mars's electromagnetic environment responds. Coordination between Earth-based observers and Mars mission teams allows cross-correlation of datasets. If MAVEN detects magnetic field disturbances at a specific time, observers can examine comet spectra or radio emissions at corresponding times, searching for correlations. If Perseverance's radiation detector shows unusual readings, ground-based observers can check whether solar activity or other space weather events might explain the anomaly. The combination of perspectives strengthens interpretations. The observations continue through late January and into February as the comet approaches perihelion. Brightness increases. Outgassing intensifies. The tails grow longer and more prominent. By late February, the comet may become visible to naked eyes from dark locations. A faint fuzzy star low in the evening sky for Northern Hemisphere observers. Then the comet will recede, fading as it climbs outward from the Sun, eventually dropping below detection thresholds of even large telescopes. Years later, astronomers will still analyze archived data from the 3 I/8less apparition, searching for subtle details missed in initial examinations. The observations become a permanent record, available for reanalysis as techniques improve and theories evolve. The comet itself, meanwhile, will be millions of astronomical units away, traveling through interstellar space at 11 kilometers per second, unreachable and unobservable. Its brief interaction with our solar system complete. The comet departs toward outer darkness with the same inevitability that governed its arrival. The hyperbolic trajectory permits no capture, no return. every hour carries the nucleus thousands of kilometers farther from the Sun. The gravitational binding weakens continuously. By the time the comet passes Jupiter's orbital distance in late 2025, solar gravity has already lost its ability to significantly deflect the trajectory. The path curves gently around the Sun and straightens into a line extending toward infinity. The outbound journey mirrors the inbound, reversed in time. Perihelion passage in late February marks the turnaround point where heliocentric distance reaches its minimum and then begins increasing. The comet was at 0.54 astronomical units from the Sun at perihelion, roughly halfway between the orbits of Venus and Earth. Solar heating peaked. Outgassing reached maximum intensity. The coma expanded to its largest extent. Then the recession began. Sublimation declines as solar radiation weakens with distance. The inverse square law governs this cooling: double the distance, and received solar energy drops to 1/4. By the time the comet crosses Earth's orbital radius outbound in March 2025, solar flux has already diminished to levels where only the most volatile ices continue sublimating. Water ice, requiring higher temperatures for rapid sublimation, begins to freeze lock. The water component of outgassing drops sharply. Carbon monoxide, with its lower sublimation temperature, persists longer. CO continues outgassing well beyond Earth's orbit, sustaining a residual coma even as the comet passes Mars's orbital distance outbound in May. But eventually, even carbon monoxide sublimation ceases. Beyond perhaps 3 or 4 astronomical units from the Sun, the nucleus surface becomes cold enough that all outgassing stops, the coma dissipates, the tails vanish. The comet returns to its dormant state. The transition from active to dormant happens gradually, not at a sharp boundary. Different regions of the nucleus stop outgassing at different distances depending on local composition and orientation toward the Sun. Some areas might retain exposed volatile ices that continue sublimating weakly even far from the Sun. Other areas develop non-volatile crusts, layers of dust and refractory organics left behind when ices sublimate, that insulate underlying ice and prevent further outgassing. As the comet crosses the asteroid belt outbound, it becomes indistinguishable from an asteroid to casual observation. No coma, no tail, just a dark nucleus reflecting a tiny fraction of incident sunlight. Its apparent brightness fades rapidly due to both increasing distance from the Sun and increasing distance from Earth. By mid-2025, the comet drops below magnitude 20, accessible only to the largest professional telescopes. By late 2025, it fades beyond even those detection limits. Jupiter, the solar system's most massive planet, exerts gravitational influence on the outbound comet. The encounter geometry determines whether Jupiter accelerates or decelerates the comet. For 3I/Atlas, orbital calculations show Jupiter will provide a slight gravitational assist, adding perhaps half a kilometer per second to the comet's departure velocity. This small boost makes no qualitative difference. The comet was departing anyway, but it does shorten the time required to reach the outer solar system. The comet crosses Saturn's orbital distance in 2027, Uranus's orbit in 2032, Neptune's in 2038. These crossings occur without fanfare. The comet passes through the empty space. The giant planets sit elsewhere in their orbits, separated from the comet's trajectory by billions of kilometers. No encounters occur. The comet simply reaches and passes each orbital radius at times determined by its velocity and trajectory. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending from 30 to 50 astronomical units from the Sun. The comet passes through this region in the 2040 S, traveling at roughly 30 kilometers per second relative to the Sun. It overtakes Kuiper Belt objects, which orbit slowly in roughly circular paths. The comet's hyperbolic trajectory takes it through the belt in a few years, a transient visitor among permanent residents. Beyond the Kuiper belt lies the scattered disk, a more diffuse region extending to perhaps 100 astronomical units. Beyond that, the solar gravitational influence continues weakening. At some distance, perhaps 1,000 astronomical units, perhaps 10,000, the Sun's gravity becomes comparable to gravitational perturbations from nearby stars. The solar system's boundary blurs into the interstellar medium without sharp demarcation. The Oort cloud, a theoretical shell of comets surrounding the solar system at distances from 2,000 to 100,000 astronomical units, may or may not exist, as observations cannot confirm it directly. If it exists, the comet will pass through it in thousands of years, moving rapidly compared to Oort cloud objects, which orbit the Sun at velocities of a few meters per second. The comet will not linger. It possesses escape velocity and will not be captured. Eventually, perhaps 20,000 years from now, the comet will reach distances where the Sun's light becomes indistinguishable from other stars in the sky. The Sun will appear as a bright star, brighter than any other, but no longer obviously special. The comet will continue outward, its velocity essentially constant at 11 kilometers per second, plus whatever gravitational perturbations accumulated during solar system passage. The nucleus will remain frozen. No star will approach closely enough to warm it again. Statistically speaking, the comet formed in a molecular cloud, wandered through interstellar space, passed once through our solar system, and will now wander through interstellar space forever. The probability of encountering another stellar system within the next billion years calculates to perhaps a few percent. Most likely. The comet will travel through the void indefinitely. Its trajectory carries it roughly toward the constellation Lyra, as seen from Earth, the same direction from which it arrived. More or less, this is not quite accurate. The Sun's motion through the galaxy and the comet's deflection during solar system passage change the outbound direction slightly from the inbound. But, broadly speaking, the comet returns toward the same region of space from which it came. Whether other comets from the same birth cloud exist cannot be known. Perhaps billions of comets formed in that molecular cloud and dispersed through the galaxy. Perhaps 3I/Atlas was ejected from a young planetary system and represents the only such object from its source region. The ice remembers nothing. The trajectory reveals nothing about siblings or origins beyond general direction. The departure proceeds without ceremony. No spacecraft will follow. No telescope will track the fading point of light beyond current detection limits. The comet will vanish from human awareness, continuing its journey unknowable and unobserved. It will pass through space for millions of years, carrying its frozen cargo of interstellar ice and organic molecules, a dark speck traversing the galaxy at velocities typical of stellar orbital motion. In one sense, the encounter with our solar system represented an anomaly in the comet's existence, a brief 3 or 4 years of warmth and activity interrupting billions of years of cold dormancy. In another sense, the encounter meant nothing. The comet was not transformed. Its bulk composition remains unchanged. It gained thermal energy temporarily and lost some mass to outgassing. But the nucleus survives essentially intact. It will continue as it was before, frozen and dark, traveling outward into darkness that has no end. Mars returns to atmospheric equilibrium within hours of closest approach. Though equilibrium overstates the stability of an ionosphere in continuous flux, the plasma density, temperature, and composition fluctuate constantly in response to solar ultraviolet flux, solar wind pressure, and internal atmospheric dynamics. The ionosphere never settles into true steady state, but rather maintains a dynamic balance between creation and loss processes. MAVEN's measurements during the encounter window show variations consistent with normal ionospheric behavior. Electron density peaks near 130 kilometers altitude at approximately 200,000 electrons per cubic centimeter during the spacecraft's dayside ionospheric passes. This value lies within the expected range for the season, solar zenith angle, and prevailing solar activity levels. The vertical density profile matches hundreds of previous measurements. The magnetometer records the draped interplanetary magnetic field configuration around Mars without significant anomalies. Field strength at 4,000 kilometers altitude, well above the ionosphere but still within the induced magnetosphere, measures approximately 15 nanoteslas, typical for moderate solar wind dynamic pressure. Field direction varies with the spacecraft's position around Mars, but follows patterns consistent with standard draping geometry. If electromagnetic disturbances from the comet's passage reached Mars, they remain below detection thresholds or indistinguishable from normal variability. The ionosphere experiences fluctuations every day driven by waves propagating from below, by solar wind pressure variations, and by crustal magnetic field geometry. Distinguishing a comet-related signal from background noise would require statistical analysis comparing many measurements during the encounter window with baseline statistics from non-encounter periods. Initial quick-look analysis by mission scientists reveals no obvious anomalies. The data appear nominal. MAVEN continues its routine measurements without triggering any automated alarms or flagging unusual conditions. This does not definitively prove no interaction occurred. Subtle effects might emerge only after detailed analysis, but it suggests any coupling between Comet and Mars remained weak. Perseverance's radiation detector on the surface shows dose rates fluctuating around typical values. Galactic cosmic rays provide steady background radiation at approximately 0.2 millisieverts per day. Small variations occur hour to hour and day to day as atmospheric pressure changes. Higher pressure means more shielding and slightly lower dose rates. During the encounter window, recorded dose rates remain within normal variability. The absence of a clear signal does not surprise mission scientists. Theoretical models predicted weak or negligible interaction given the 13 million kilometer separation. Electromagnetic coupling across such distances requires specific field line geometries that may not have occurred. The comet's induced magnetosphere, while extensive on its own scale, remains small compared to the separation distance. The ionosphere, for its part, continues losing material to space at rates unchanged by the encounter. Pickup ions, atoms from the upper atmosphere, ionized by solar ultraviolet and then picked up by the solar wind, escape continuously. Solar wind impacts strip atmospheric molecules directly. Approximately 100 grams per second depart Mars permanently, carrying away atmosphere particle by particle. This erosion has proceeded for billions of years and will continue for billions more. The planet completes its rotation, bringing different longitudes beneath the ionospheric peak. Local morning transitions to afternoon. Shadows lengthen across Jezero crater as evening approaches at Perseverance's location. The rover executes its programmed activities, analyzing rock compositions, imaging geological formations, monitoring weather. The radiation detector continues its accumulation of dosimetry data, adding January 19th to its multi-year record. Above, MAVEN continues orbiting. The spacecraft's trajectory remains unchanged. Gravitational effects from the comet were negligible as expected. Orbital period holds at 4 hours and 32 minutes. Periapsis altitude maintains at 150 kilometers. The spacecraft's instruments continue their measurements, sampling the upper atmosphere and magnetic environment with the same reliability they have demonstrated since 2014. The crustal magnetic anomalies create their localized field structures unchanged. The mini-magnetospheres persist, deflecting solar wind slightly, contributing to the complex topology of field lines draped around the planet. Reconnection events occur sporadically as they always do, driven by solar wind variations and rotational changes in interplanetary magnetic field direction. The rate of reconnection during the encounter window shows no statistical deviation from typical rates. The lower atmosphere, far below the ionosphere, remains entirely unaffected. Surface pressure at Jezero crater measures 650 pascals on January 19th, varying by a few percent with the daily temperature cycle. Winds blow at a few meters per second. Dust devils spiral across distant plains. Weather patterns proceed according to seasonal norms, driven by solar heating and atmospheric circulation. No trace of the comet's passage appears at the surface. In the weeks following the encounter, as data downloads to Earth and scientists examine detailed time series, the conclusion solidifies. No measurable interaction occurred. The comet passed Mars electromagnetically isolated despite their relative proximity. The 13 million kilometers proved sufficient separation to preclude coupling. The encounter, anticipated but uncertain in outcome, produced null results. Null results possess scientific value. They constrain models, eliminating parameter ranges that predict detectable effects. They confirm scaling laws that predict interaction strength falls off rapidly with distance. They provide comparison data for future encounters should another interstellar comet pass near a planet at different separation or with different magnetic field configuration. The data enters archives alongside 10 years of previous MAVEN measurements and 8 years of Perseverance surface data. Future researchers analyzing atmospheric escape processes or ionospheric dynamics will include January 19, 2025 in their datasets without special consideration. The day becomes one data point among tens of thousands, notable only for what did not occur rather than what did. Mars continues its orbit. Indifferent. The ionosphere continues its cycle of creation and destruction with each sunrise and sunset. The solar wind continues eroding the atmosphere grain by grain. The red planet proceeds through its 687-day year toward northern summer, when the polar carbon dioxide cap will shrink to minimum extent and atmospheric pressure will reach annual maximum values. The comet, meanwhile, recedes outward past Jupiter's orbit, dimming beyond detection, carrying its frozen chemistry toward interstellar space. The brief proximity to Mars, 13 million kilometers at closest approach, becomes a footnote in its billion-year journey. The planet affected the comet not at all. The comet affected the planet not at all. They passed in space. Two objects following separate mathematics through vacuum. Their trajectories intersecting in time but not in consequence. Implications for planetary science emerge slowly from the encounter's null results. The absence of detectable electromagnetic interaction at 13 million kilometers provides a data point constraining models of how cometary-induced magnetospheres couple to planetary environments. Theoretical predictions suggested interaction remained possible if magnetic field line geometry permitted connection. Observations indicate either the geometry was unfavorable or the models overestimated coupling efficiency at large separations. The finding contributes to understanding similar encounters that might occur elsewhere in the solar system or around other stars. Jupiter possesses a powerful intrinsic magnetic field extending millions of kilometers into space. If an interstellar comet passed Jupiter at 13 million kilometers, would electromagnetic interaction occur? Mars's lack of global field makes it a different case, but the scaling laws governing electromagnetic coupling should apply universally. Spacecraft missions to other solar system bodies occasionally encounter transient populations of dust and plasma from comets or asteroids. Understanding how these populations interact with planetary magnetospheres and ionospheres helps interpret measurements and predict space weather effects. The Mars 3 I/Atlas non-encounter adds to the empirical database informing such predictions. Atmospheric escape from Mars continues receiving research attention. Approximately 3 to 4 billion years ago, Mars likely possessed a much thicker atmosphere, possibly dense enough to support liquid water on the surface. Geological evidence suggests ancient river valleys, lake beds, and perhaps even oceans. Today's thin atmosphere cannot support liquid water except transiently under specific conditions. Where did the atmosphere go? Solar wind erosion provides part of the answer. Without a protective magnetic field, Mars's atmosphere has been stripped away over billions of years. MAVEN's measurements quantify current escape rates, about 100 grams per second through various processes including ion pickup, sputtering, and photochemical escape, integrated over 4 billion years. This rate could remove an amount of atmosphere consistent with geological estimates of past atmospheric density, but uncertainties remain. Escape rates likely varied over time as solar wind conditions changed and Mars's own magnetic field declined. Early in solar system history, the young sun emitted stronger stellar winds. Mars's atmosphere faced more intense erosion then. As the sun aged and solar wind weakened, escape rates declined. Quantifying these historical variations requires models calibrated against modern measurements. The comet encounter, despite producing no detectable effects, provides a test case for understanding transient perturbations to escape processes. If a comet passing 13 million kilometers cannot measurably affect atmospheric escape, then only much closer encounters or much larger objects would matter. This constrains scenarios in which comets or asteroids might have contributed to or removed atmosphere through electromagnetic interactions. Interstellar comet composition remains a topic of high interest. Each new interstellar object detected offers a sample of material formed in another stellar system, providing comparative data to solar system objects. So far, the few interstellar comets observed, 1I/Oumuamua, 2I/Borisov, and 3I/Atlas, show diverse properties. Oumuamua exhibited unusual acceleration suggestive of outgassing but showed no detectable coma or tail. Borisov appeared remarkably similar to solar system comets in composition and behavior. 3I/Atlas falls somewhere between, showing moderate activity and composition broadly consistent with solar system comets, but with some isotopic peculiarities. The diversity suggests either that comet formation processes vary among stellar systems, or that our sample size remains too small to reveal underlying patterns. Detecting more interstellar objects would help answer this question. Current estimates suggest 1 or 2 interstellar comets pass through the inner solar system per year, but most remain too faint for detection. Improved survey telescopes, particularly the Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, should detect interstellar objects more frequently. Each detection offers opportunities for intensive study. Spectroscopic observations constrain composition. Photometric monitoring reveals rotation periods and nucleus sizes. Orbital calculations determine trajectories and origins as precisely as data allow. And if an interstellar object happens to pass near a planet with orbiting spacecraft, in situ measurements become possible even without dedicated missions. The Mars 3Y/Atlas encounter represents one such opportunity that occurred but yielded minimal data due to the large separation. Future encounters might prove more favorable. An interstellar comet passing within 1 million kilometers of a planet would almost certainly produce detectable electromagnetic effects. One passing within 100,000 kilometers might directly interact with the planet's atmosphere, depositing cometary material or triggering auroral emissions. Such close encounters remain rare. The solar system is mostly empty space. Random trajectories seldom bring objects near planets, but over long timescales, close encounters become probable. Venus, Earth, Mars, and Jupiter have all likely experienced interstellar comet passages at various distances throughout their histories. Most went unobserved and unrecorded. A few might have left traces in geological or ice core records if material deposition occurred. Looking forward, planetary scientists anticipate future interstellar object detections and plan strategies for rapid response observations. When a new object appears in telescope surveys, its trajectory must be calculated quickly to determine whether planetary encounters might occur. If an encounter seems likely, spacecraft instruments can be retasked to make appropriate measurements. Ground-based observers can coordinate campaigns. The infrastructure exists, only opportunity is required. The study of interstellar objects also informs astrobiology. If comets carry organic molecules between stellar systems, they might transport prebiotic chemistry or even microbial life across interstellar distances. This panspermia hypothesis remains speculative, but interstellar comets demonstrate that material exchange between stellar systems occurs naturally. Whether that material could harbor life or life's precursors depends on survival during millions of years of interstellar transit. Laboratory studies suggest some microorganisms could survive such journeys if protected within comet nuclei. Cosmic ray radiation would sterilize surface layers, but several meters of ice and rock would provide shielding. Internal temperatures would remain near absolute zero, preserving frozen organisms indefinitely. Upon entering a new stellar system and approaching the star, thawing might revive dormant life. No evidence currently supports active panspermia, but the possibility remains open for investigation. Future sample return missions to comets might search for biological signatures. Interstellar comets would be prime targets for such searches, though the difficulty of reaching them with spacecraft makes such missions technically challenging and expensive. The Mars 3 I/Atlas encounter contributes a small piece to this larger puzzle. The lack of interaction confirms that electromagnetic coupling at large distances remains negligible. The observations add to data sets documenting how planetary environments respond, or fail to respond, to transient perturbations. The measurements join archives that future scientists will mine for patterns and anomalies. Science proceeds incrementally. Each observation, each null result, each confirmed prediction or surprising anomaly adds to collective knowledge. The comet's passage past Mars generated data. That data becomes part of the permanent record, available for reanalysis as theories develop and questions evolve. The encounter is over, but its contribution to understanding persists. The comet moves outward through darkness now, beyond Jupiter, beyond Saturn, toward the outer reaches where sunlight dims to starlight and cold returns absolute. The nucleus spins in silence, its rotation unaffected by the brief warmth of perihelion. Ice remains frozen on surfaces that never faced the sun. Dust settled into crevices during outgassing will remain there, undisturbed as the object travels for millions of years through the void between stars. Mars continues its orbit, its ionosphere rising and falling with each sunrise and sunset, its atmosphere escaping molecule by molecule into space. The processes that shape the planet proceed without interruption. Dust storms will come and go. Polar caps will advance and retreat with the seasons. Rovers will drill into ancient rocks, searching for signs of past life that may or may not have existed. Orbiters will measure and transmit data until their systems fail and they fall silent. The encounter occurred but left no mark. No crater formed. No atmospheric disturbance persisted. No magnetic field retained memory of the passing. January 19th, 2025 became simply another day in the measurement record, its data indistinguishable from days before and after. The comet and planet approached, reached minimum separation and diverged, governed entirely by gravity and momentum, affected by nothing beyond physics. In the archives, the data waits, numbers in files on servers, backed up and distributed across multiple locations for preservation. electron densities measured at specific times and altitudes, magnetic field vectors recorded at 8 samples per second, radiation dose rates accumulated minute by minute, all of it stored, catalogued, available for analysis now or decades hence when new questions emerge and old data gains new relevance. The universe continues its expansion. Galaxies receding from one another at velocities determined by distances and the Hubble constant. Stars form and die. Molecular clouds collapse and disperse. Comets form and wander. Planets orbit their stars through billions of years, gaining and losing atmospheres, warming and cooling as stellar evolution proceeds. None of it requires observation. All of it continues regardless. The silence of space persists, unbroken by any sound, filled only with electromagnetic radiation and the slow trajectories of matter through vacuum. The comet falls outward into that silence. Mars rotates within it. Both objects follow paths determined long ago by initial conditions and physical laws. Both will continue until perturbations alter their trajectories or until time itself ends. Whichever comes first. For now, there is only the motion. The slow recession of a dark nucleus carrying its frozen chemistry toward infinity. The patient rotation of a red planet beneath a thin sky. The measurements continuing, data accumulating, knowledge growing, grain by grain. And beneath it all, the fundamental silence of vacuum, older than stars, extending everywhere light cannot reach. The stillness remains absolute. The darkness remains complete. The cold returns and stays.